Hey friends, I'm standing here today in beautiful Carrollton, Georgia to talk to you about a problem that faces 25% of Americans and hundreds of millions, in fact billions of people around the world. What I'm talking about today is how to return wastewater to the environment without the means of a sophisticated central sewage treatment plant. Specifically, I'm talking about septic systems. Now, this is inherently a geotechnical problem. It's a problem that we're going to face in our lifetime as a growing problem as more people end the practice of open defecation and they begin to treat sewage via crude septic types, septic systems, all sorts of crude measures that have been invented all around the world to deal with this problem. It's a problem that affects human health, liveliness, well-being, and it has many knock-on effects as we improve the quality of life moving forward in the 21st century. Now you'll notice I'm holding here today my trusty probe rod. Now this is the most sophisticated instrument in all of geotechnical engineering, except for all the others. Now, one thing you're going to notice when you're standing in a septic field like I am here today is that the soil is very easy to penetrate. This is basically just a miniature cone penetrometer, and you're going to find that it's very easy to penetrate the soil. This is going to have a lot of impacts as we talk about the limitations of septic systems in urban environments. Now, for those unfamiliar, a septic system takes all the waste that comes out of the house under gravity flow, and instead of connecting to a municipal sewage treatment system, and all the collectors and feeders that go to it, it's going to take all the sewage that's coming out of the house and it's going to feed it into the primary system, which is called a septic tank. Now this depends on the size of the house, and I'm going to show you some graphics to talk about the different design criteria, but generally it depends on the number of people that use that system. So after the septic tank, most of the solids are going to settle into the tank, and the water that's skimmed off the top goes into what's called the septic drain field. Now the septic drain field is the primary interaction with the wastewater and the soil. Now again, this is an inherently geotechnical problem. So once you have the water that's coming out into the septic drain field, which again is a hydraulic field, you can see the gradient that goes in response to the total head. This water is going to flow downhill. So you have these thin tubes that are carrying water into the septic drain field are going to be packed in a bedding sand that are going to host some of the microorganisms, but then it's going to return to the native soil. And this is the primary host for the microorganisms. They're going to turn our wastewater into something that's suitable to flow back through all the channels into the protected waters behind me. And these waters are important for recreation, they're important as a potable water source, and they're important for navigation. So obviously you see behind me, this is Sharps Creek Reservoir. This is not a navigable waterway, but it is important both for recreation and as a potable water source. So I couldn't find a better site to show you how important it is to do this well, because you have wastewater in close proximity to an important water source.
Okay, let's back up to that last frame because I promised you graphics on a septic system schematic. So here we go. First thing you should notice is that this is a hydraulic system. Our wastewater responds to the total head in the system, which leads from the house in the upper left down the slope to your screen's low right corner. Another hydrodynamic feature we want to put to work for us here is the settlement velocity for our flocculated and coagulated solids. We want to settle these out into the septic tank here for continued digestion, while the mostly clean, skimmed water can progress to the absorption field, just like it would in the primary clarifying basin in a wastewater treatment plant. The next thing we need to recognize is that we have chemicals in this hydraulic system besides organic waste and water. A lot of chemicals. Some of these chemicals have some pretty violent chemistry, but you're not thinking about that because they come in clever, attractive bottles as they sit on the store shelf, and besides, they do some pretty useful things for us, like wash our clothes or clean our toilets. To understand what this is doing to our soils, we need to think like a particle. So, follow me to the lab. Welcome to the lab. This is our test subject, a South Georgia kaolinite sample, which will be prepared as a solution with tap water, then have a parade of chemicals thrown at it, just like we would do to it if this were our septic absorption field. Now, it's true that kaolinite is not a common backyard find, but its chemistry is well documented in literature, and its sensitivity is analogous to soils that we do find all over the world. So let's get started. So our kaolinite is prepared as 8 specimens of 50 grams dry soil and 150 milliliters of regular city tap water. Each chemical is diluted as it would be per recommended use on the bottle, then poured, flushed, or rinsed through our 1,000-gallon septic tank. And finally introduced to our specimens carefully with a pipette for a particle level chemistry brawl. Now let's see what happened.
Okay, this is 48 hours post-contact here, so we're going to go up and down the line here and show you from the side and from above what each of these looks like. This first one is our control sample. This is just the regular kaolinite in solution. Now we have Tide laundry detergent. Notice the turbidity that we see in this. This is also an alkaline sample, as is the Lysol here that's next to number 3, but the turbidity is what's surprising in the Tide. And so now we come to number 4 is Lime Away, which is handy at removing lime scale off of hard ceramic surfaces. And so up number 5 is Vinegar. This is a common household item for cleaning. Obviously, it also has uses in the kitchen too, but it's widely used. Number 6 is the first of our oil-based cleaners. It's particularly toxic, but it could end up in your septic system. So we went ahead and looked at it. Ammonia's next, and again, we see the turbidity here. It's not a consistent theme among the alkalines, but it certainly happened among the two. WD-40 is last, and again, this is an oil-based cleaner. So this is 48 hours post-contact, and now we're going to show you some close-up stills to see exactly what happened and look at some chemistry. So now brought us in for some close-ups here, and also to bring the summary chart back, you can see some of the results. In fact, notice some of the gas bubbles that have formed in some of them. That was a really striking result. pH doesn't explain all of this, as you can see, but we absolutely have effects caused by the excess salts that are going to be precipitated by all these reactions, and there's certainly a diffuse double layer that is absolutely going to be affected over even the short term and certainly the long term, but definitely in engineering timescales that are clearly affected by these clay particles and their sensitivity. I would like to bring your attention back to the fact that we have a living thing on our hands. So if you thought the clay particles had it bad, think about the bacteria, the bugs as they call it in the wastewater treatment business. The bugs have to withstand all this chemical and biological torture as well. And in a similar experiment, it's true that you can chemically peel an egg. In lemon juice, it takes just under an hour and it will totally ruin your egg.